Bismillahirrahmanirrahim. Hello students, welcome to the Electrical Engineering channel. In this lecture, I am going to discuss the energy density associated with electrostatic fields. So, in deriving the total potential energy of combination of point charges or a volume charge distribution, we have to assume that initially in the considered volume, there is no charge present and n charges are brought from infinity to the selected volume one by one, right? So initially this space is empty and we are starting to accumulate charges one by one from taking from infinity and placing them in this volume, and the total amount of work done in placing all those charges in this volume will be equal to the total potential energy of this combination of charges, and that potential energy will be actually derived in this lecture, right? So initially when this selected volume has no charge, there will be no electric field in the initial point. So when I take the first charge q1 from infinity to this volume, I will do no work in placing that first charge from infinity to this volume, because initially the electric field at this selected volume is equal to zero. And why this electric field is equal to zero? Because there is no charge present initially in this volume. So when I place first charge q1 from infinity to this volume, I have done no work, right? So initially the volume is empty with no point charge present. Now work to position Q1 is equal to 0 because there is no electric field. Now work to position Q2 is equal to Q2 V21. So when I place the second charge Q2 from infinity to this volume, there will be some work required to do that, because now due to already present charge Q1, there will be electric field in this volume, and whenever there is an electric field and we are moving a charge from one place to the other, some work has to be done. So in this case, work to position q2 will be equal to q2 multiplied by v21. So q2 is the magnitude of charge q2, and v21 is actually the potential at the position of q2 due to q1. Similarly, work to position Q3 is equal to Q3V31 plus Q3V32. Now Q3 is the magnitude of third charge and V31 is the potential at the position of Q3 due to Q1 plus Q3 multiplied by V32, potential at the position of Q3 due to Q2. So when I have moved the third charge Q3 in this volume, there are two charges already present in this volume. So the influence of charge, first charge will be present and the influence of second charge will also be present over here. So we have to add the influence of both already present charges. Similarly, when I position the fourth charge Q2, then the total work done will be equal to Q4V41 plus Q4V42 plus Q4V43. So in carrying the total work in carrying all the charges will be equal to the sum of these works, right? So this is the first work expression q2 v21 plus q3 v31 plus q3 v32 plus q4 v41 plus q4 v42 plus q4 v43. So this is my first expression, which is equation 1. Now q3 v31 can be written as q3 multiplied by v31, which is actually the potential at the position of q3 due to q1. So that will be equal to q1 over 4 by epsilon r13, and this whole expression can be written as q1 multiplied by q3 divided by 4 by epsilon r31, and this will be equal to q1 v13, right? So we can invert all these expressions in equation 1. So in this case, total work WE will be equal to Q1 V12 plus Q1 V13 plus Q1 V14 plus Q2 V23 plus Q2 V24 plus Q3 V34 plus so on. Now I have obtained second equation and we can add equation 1 and equation 2. So upon adding equations 1 and equation 2, we will have 2we, right? This is we, this is also we, which is by mistake written as w3. This is also we. So 2we will be equal to q1 into v12 plus v13 plus v14 plus so on, plus q2 into v21 plus v23 plus v24 plus so on. Similarly, plus q3 into v31, right? This is v31 plus v32 plus v34 plus so on and so on. So this whole expression can be written as 2we equal to q1 into v1 plus q2 into v2 plus q3 into v3. So v1 is actually total potential at the position of q1. This is total potential at the position of q2 due to all other charges. This is total potential at the position of q3 due to all other charges plus so on. And this summation can be written as we equal to 1 by 2 summation m is equal to 1 to n qmvm. So for n charges, this can be written in the form of a summation. For a continuous volume charge distribution, this summation will become an integral, and we will be equal to 1 by 2 volume integral uh, q is equal to rho v dv, right? This q will be equal to total charge and it will be equal to rho v dv, and this is the potential v. So q is equal to rho v dv, and this expression can be written as rho v is equal to del dot d. So del dot d is equal to volume charge density. This is the Maxwell's first equation, which we studied in the third chapter. So that will be equal to 1 by 2 del dot d into v into dv. Now we will use a property of this vector operator, and that property is actually del dot vd is equal to v into del dot d plus d dot del v. So del dot d into v, because we need del dot d into v over here. So del dot d into v will be equal to del dot vd minus d dot del v. So it will become minus when we shift this expression to the left hand side. So it will be minus d dot del v. So put this expression in place of del dot dv. So we will get 1 by 2 volume integral del dot vd dv minus 1 by 2 d dot del v dv. So according to divergence theorem, this del dot vd is equal to vd dot ds, right? According to divergence theorem. So this will be equal to vd dot ds closed surface integral, and this expression will be minus 1 by 2 d dot del v dv, and this is volume integral. Now this is a closed surface integral, and this expression also has a potential. So whenever we have a potential in the integration and that integration is taken for a closed surface, that will be equal to zero, because potential in any closed path is always equal to zero, because potential is also a form of work done. So work done along a closed path is always equal to zero. So here we have a closed surface integral, and that expression will be equal to zero. And uh, we also know that uh, E is equal to minus gradient of V minus del V. So this is del V, and it can be replaced with minus E. So minus minus will be equal to plus, and it will become 1 by 2 d dot E dV. So this is the expression for the energy of a volume charge distribution, and that is equal to 1 by 2 volume integral d dot E dV. And we can further simplify this expression by assuming that d is equal to epsilon E, right? So it will become epsilon E dot E, and E dot E will be equal to E square. And this is another expression for the energy due to electrostatic field. And if we take the derivative of this energy, we will have dWe divided by dV, and that will be equal to 1 by 2 epsilon E square. And this expression is called energy density in the electrostatic fields, right? So because this is energy per unit volume, so half epsilon E square is energy density, and total energy will be evaluated by taking the volume integral of this expression. So total energy of the charges is equal to total work done to place them. So as I told in the start of this lecture that total energy of this volume charge distribution will be equal to the total amount of work done in bringing all the charges from infinity to this selected volume. So this is how we can derive this expression for the total energy. Now I will solve a few examples to calculate the electric fields, potentials and energies due to electrostatic fields. So we are given the expression of a volume and we are given this region, this volume, right? And we are asked to evaluate the energy. So energy is equal to half epsilon E square dV, and we are given V over here, so we can easily calculate E. E is equal to minus del V, so it will be minus partial over partial R, 200 over R, so it will be 200 over R square, and we can evaluate this integration easily. So E square will be equal to E dot E, right? And it will be 40,000 divided by R raised to power 4. And just put this expression over here. This is E square. And after simplification, it will become 17.7 into 10 to power minus 8. This is the volume integral and the range of all the three components is given. So just evaluate this integral. 1 over r square integral is minus 1 over r. So integral of sine theta is minus cos theta. And when we put the limits from 0 to pi by 2, minus cos theta will be equal to 1. Similarly, for d phi, we will get pi by 2. So here we have pi by 2. This is 17.7 into 10 to minus 8. And here we have minus 1 over r. After putting these limits 2 millimeter to 3 millimeters, we will get this answer. Now I will solve end problem 4.19. And in this problem, we are given a surface charge density 5 rho nanocoulomb per meter square for a region of rho between 1 centimeter and 3 centimeter, and z is equal to 0. So let's calculate the potential at point 0, 0 into 2 centimeter. So this point is located at the z-axis, and we are also given that v is equal to 0 at infinity. So v at this point is equal to surface integral of rho s ds divided by 4 pi epsilon r minus r dash magnitude, and this is the integration for phi, and this is the integration for rho, and here we will have rho d phi, right? So 5 rho into rho d phi will become 5 rho square into 10 to minus 9, because this is a nanocoulomb per meter square charge density divided by 4 by epsilon into rho square plus z square under root. So this integration is going to be very lengthy, so I suggest all of the students to pay full attention to the evaluation of this integration. And v at p will be equal to 45 into 2 pi, and this integration from 0.01 to 0.03 rho square d rho divided by rho square plus g square. So this integration can be evaluated by assuming this substitution: rho is equal to z tangent theta, d rho is equal to z secant square theta d theta. Let's put all these values over here, and after simplification we will have 1 plus tangent square theta under root over here, and it will become secant theta. So secant theta will be cancelled out with this secant square theta, so it will become z square tangent square theta secant theta d theta. And after simplification, this can be written as sine square theta over cos cube theta, and sine square theta is equal to 1 minus cos square theta divided by cos cube theta. This is z square, and it can be separately written as z square secant cube theta integration minus z square cos square theta over cos cube theta. So it will become secant theta d theta. So the integration of secant theta is equal to natural log of tangent theta plus secant theta. So this is very simple, but the integration of secant cube theta will be tricky. So let's apply integration by parts, and secant cube theta can be written as secant theta into secant square theta d theta. So secant theta can be made as first function, secant square theta can be made as second function, and while evaluating integration by parts, we will use first function into integral of second minus integral of second into derivative of first. So this is first function. This is the integral of the second function secant square theta minus integral and integral of second function which is tangent theta into derivative of the first function. So derivative of secant theta is secant theta tangent theta, and here we have d theta. So let's evaluate the integration of this expression again, and it will be secant cube theta plus secant theta d theta. So this thing actually is coming secant theta tangent square theta d theta. So this expression is coming again from this expression. Here we had secant theta tangent square theta d theta. Again we obtained secant theta tangent square theta d theta. So this expression can be written as uh, secant cube theta, right? Secant cube theta and secant theta. So this expression is actually composed of two separate integrations of secant cube theta minus secant theta. Since we have minus sign over here, so we will have minus sign with this secant cube theta d theta integration and plus sign with this secant theta integration. Now this secant cube theta can be taken to the left hand side because at the left hand side we have integration of secant cube theta d theta. So it will become 2 integration of secant cube theta d theta, and here we have this expression and the integration of this expression. So integration of this expression is this, and we can divide this right hand side by 2 to evaluate the integration of secant cube theta. So integration of secant cube theta is equal to 1 by 2 secant theta tangent theta plus 1 by 2 natural log of tangent theta plus secant theta, and we can put all these answers, all these evaluations in this expression, right? So the integration of this expression finally will be equal to z square over 2 secant theta tangent theta plus z square over 2 natural log of this minus z square natural log of this. So these two expressions can be simplified further, and they will be equal to minus z square over 2 natural log of tangent theta plus secant theta, and here we have this expression. So now let's perform the back substitution, and initially we substituted rho equal to z tangent theta. It means this is the triangle. So from this triangle, tangent theta is equal to rho over z, and secant theta is equal to rho square plus z square under root over z. So let's put these values of tangent theta and secant theta in this equation. So this is the next step, and we will do some cancellations. And after these cancellations, we will get this expression. Now let's put the limits of z from 0.01 up to 0.03. So when we put these limits and when we put the value of z equal to 0.02, we will get this answer. So this is the potential at point P, which is equal to 0.0265. So I recommend all of you students to solve this problem by yourself and do the practice of this integration, and that will be very helpful for you. So I hope you have understood the concept discussed in this lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.